Welcome to the AI Safety Reading Group. This is session number 191, and today we're reading Pessimisms About Unknown Unknowns Inspires Conservatism by Michael Cohen and Marcus Hutter. So quickly, we'll just go over the 2x2 matrix, which will define what the paper is going to talk about. So there are these top items here, knowns and unknowns, and then there's knowns and unknowns. So known knowns, things that you're aware of and that you know you're aware of. Then there's unknowns, unknown knowns, things that you're not aware that you know, but that you understand. Similarly for known unknowns, but today we're focusing on unknown unknowns in the context of artificial systems. There's something a system is not aware of in which it doesn't necessarily understand. And that can be rather precarious because it can lead to consequences which you couldn't see. So a background on the authors of this paper: Michael Cohen is a DPhil student in engineering sciences at the University of Oxford. It's equivalent to a PhD student, so he's getting a research doctorate, and his studentship is funded by the Future of Humanity Institute. And the other co-author on this paper is Marcus Hutter. He's a senior research scientist at DeepMind in the United Kingdom. Formerly, he was a professor at Australian National University, and he was the creator of the AXI, or AI Chai model, which is a theoretical model for superintelligence, which is the foundation for this paper. He was also a researcher at IDSIA in Switzerland with Jürgen Schmidhuber, during which he supervised Shane Legg's PhD thesis, who went on to co-found DeepMind after working at University College London. So that's background on the authors. They've been working together for about 2 years now, prior to going to Oxford and London, respectively. So this paper is a technical paper with formal solutions, which means mathematical proofs. Today, I'm really only going to be discussing pages 1 through 13 with proofs omitted. And that choice was made clear after my first presentation and after reading the less wrong and alignment form comment that Michael Cohen added from his supervisor, where Marcus said, just a warning, this paper is dense. I was sweating blood. Or at least Cohen said the first part and Hutter said the second part. So we won't have time to go through the proofs, but if you have questions, there are some resources at the end and we can discuss them as necessary. So in the abstract, they begin with the problem statement, which states, we do not know of any general purpose approaches in the literature to avoiding novel failure modes. So you can consider all the different ways things can go wrong in the world. We don't know how to write that down. A few weeks ago, we also had a presentation from Dr. Armstrong, also at the Future of Humanity Institute, and he argues that if you could write down every possible bad outcome, that you could create a new bad outcome which meets all of your criteria, but is bad in a different way, which could be a philosophical argument we could address later. But in this paper, they propose a solution by defining an idealized Bayesian reinforcement learner that is pessimistic. And I guess we should parse those words briefly. Idealized means you define it as perfectly, and then later you could do an approximation of a system that's not computable. Bayesian reinforcement learner. Bayesian is talking about Bayes' theorem, where you can update your priors to get a more accurate model or a more accurate probability. And reinforcement learning is based on this notion of a reward hypothesis, which conjectures that all of what is meant by goals and purposes can be thought of as the maximization of the expected value of the cumulative sum of a received scalar signal, which they call a reward. In essence, every goal can be stated as the sum of cumulative rewards. And that's what they're going to be using to formalize a solution to novel failure modes. So ergodic is a physics term that's often used by the students of Marcus Hutter, because Marcus was a physicist by training, but they're not using it in the way normal physicists use it. In this context, ergodic means that you're never going to see the same environment, or you're never going to be able to go back and redo a state in the same environment. So you can think of driving a vehicle very fast and hitting another vehicle, and perhaps somebody gets injured. They can't go, oh, that was a bad move that I turned right on red or didn't stop at some sign. Let me undo that. It's not possible. And this is one of the contexts that they introduce their problem. So they say, in a complex environment, one never or hardly ever sees the exact same state twice, or even worse, if the environment is non-stationary, a previous observation of the mentor taking an action A from states does not imply that it is still safe to do so. So they also introduced the term non-stationary. And for the context of this conversation, non-stationary is going to talk about your goal being somewhere in an environment, and that goal could move. You could think of a grid world with an agent trying to get an element in like a matrix in row 1, 1, and then you restart some game or whatever the environment is, and now the goal is in a different state from what it previously was. So doing the same action twice doesn't necessarily help. So the key technique they're using in this paper has been used previously, but it's going to be mentoring. There's this generalized agent, which they call pessimistic, and it can select an action on behalf, or there's a mentor which can select an action on behalf of the agent. The unique aspect of this paper and the previous paper by Michael Cohen is that the agent is queried less and less as time goes towards infinity, with the probability reaching 0, meaning that you're not always dependent on the mentor to have a safe system. So eventually we can get rid of the mentor or safe policy. So they also introduce properties of these pessimistic agents. And what they say here is that the value of the pessimistic agent, the expected sum of cumulative reward, is going to be greater than or equal to the value of the mentor statement. So if we wanted to analyze this as time goes towards infinity, the lowest upper or lowest greater bound would be this element over here. The value for all interaction histories of the agent with pessimism, beta, is going to have a higher value or equal to value than the mentor's policy. And policy is denoted by this symbol pi over here, and M just designates that it's the mentor. Mu is representing one of the possible environments. And H of T is saying all the things that could, or H less than T is saying all of the interaction history that happened up until that point, not including this point. So that could be your observations of the world and your rewards. So the other property of the pessimistic agent that they define is that they give it this scalar property. It's from the title of this paper, Pessimism. They define it to be a real number in an open interval. So you can see the number line below. Any of these numbers could be a pessimistic scalar, which they're defining ahead of time. So that with arbitrary high probability for the whole lifetime of the agent, if some event never happened, the agent's not going to make that event happen. And the mentor will take the agent on, or so either the agent will take the action on behalf of the mentor. Oh my gosh, I'm messing that up. Either the mentor will take an action on the agent's behalf, which makes an event happen for the first time, or the event will never happen. And the neat thing about this is that they can prove it, and they do it so in theorem 11. They call this theorem probably respecting precedent theorem. What's unique about this is it's not going to do anything that hasn't seen before, and that they explicitly defined what an event happening is or to have happened is. This is useful for when people get into philosophical arguments about what it means for an event to happen. When it's characterized mathematically, you don't have to worry about ambiguity. You might have to worry about other problems such as incomputability, but you don't have to worry about understanding what it is. So I just wanted to note an aside on their writing. A lot of papers will introduce some novel technique, but they're not quite clear about what they mean. And I wanted to give a brief excerpt of why this paper and other papers by the same authors are written so well. So they introduce a new thing. They say a policy pi and a world model V induce a probability measure P of V pi over an infinite interaction histories. And if you're like me, you read that and go, what does that mean? And the next sentence so easily follows, this is the probability of events when actions are sampled from a policy pi and observations and rewards are sampled from V. And then they define it mathematically formally. They go on to explain more, and then they also explain their limitations. So they say, we use general history-based world models with no assumptions of V in the set of world models, even though they present complications that finite state Markov ergodic models, world models do not. And this is the crux of their paper. All the other solutions to unknown novel failure methods make assumptions that they are not making, namely that it is either going to be finite state or it's going to be a finite state Markov, or it's going to be ergodic, and that's not the assumption they're making. I thought that was exceptionally well written. They have a number of theorems at the end, which tell you exactly what the properties of the agents are, but this is an executive summary of the paper. 13 pages reduces rather quickly, and that's pretty much it. The discussion is not recorded, but there is a reference slide, as well as some questions, resources. If somebody actually wanted to understand this thoroughly, you would need to know infimum and supremum from analysis. That's the INF and SUP in the paper, what a policy is, as well as some of the properties of IEC, which is listed in the final reference over here. I had some questions while I was reading the paper, namely that they didn't address what extreme pessimism being more harmful than helpful does. They reference in their literature review that another group had found that pessimism doesn't do much for you, but they didn't elaborate why, or at least I didn't see why. The other thing is they defined sets somewhat differently than previous papers, and I'm not sure if that also extends to their complexity class. I gave the easiest example that I could find, which is that they're using two different definitions for the natural numbers. And I was wondering if anyone had read the pseudocode algorithm. And that is all. Thank you for reading.